Hello viewers of mine, this is a What the Physics video. This is about universal gravitation. This is an example problem. We've got, example, that's interesting. Frank is 12 kilograms and is sitting 0.75 meters away from Sally, who is 16 kilograms. So let's go ahead and start filling those in. Frank is 12 kilograms and Sally is 16 kilograms. And the distance they are from each other, and I have this this diagram down here, the distance they are from each other is r. R stands for radial distance. In this case, it doesn't stand for radius, it stands for radial distance. Some textbooks also write it as just plain d, and that's fine too, but I'm going to use r. So that is going to be 0.75 meters. And the question is, what is this force equal to? So we've made our list and we've drawn our sketch. This is just a gravitational attraction scenario, so we're going to use Newton's law of universal gravitation. So gravitational force is equal to big G times mass 1 and mass 2, in this case mass Frank, and then this is mass Sally, divided by r squared. And like I said, some textbooks use d squared, and that's going to be fine. I don't need to rearrange anything, it's already rearranged for me, so I just need to plug in, okay? Big G in this case is not the little g like 9.8 or 1.6 like on the moon. Big G is going to be a big number that we're putting in here. It's actually a small number, but the size that I have to write out is rather lengthy, so actually I'm going to give myself a little bit more space. 6.67 times 10 to the negative 11. And then I've got some weird units. I've got Newton meters squared per kilograms squared. It's a negative 11 right there. Okay, that is the value for big G. That's the universal gravitation constant. And then we've got Frank. Frank is going to be 12 kilograms. And then we've got Sally, and Sally, we said, is 16 kilograms. And then the radial distance in between them, 0.75 meters. Now, the biggest or the most common mistake people are going to make is forgetting to square this. So I'm just going to draw in an arrow, kind of emphasizing, make sure to square it. Here, I'll even change the color. Ooh, that'll really emphasize things. Ooh. So let's go ahead and plug those numbers into our calculator. And I'm going to end up with a pretty small value. The 12 times 16 and then divided by 0.75 squared, that's not that small of a value, but it's this part right here, the times 10 to the negative 11, that just makes everything really, really small. So the force, the gravitational force between Frank and Sally is going to be 2.3 times 10 to the negative 8 newtons. So this just comes from plugging things in. A reminder on plugging things into the calculator, I would sure recommend when we're doing this section here, first of all, I talked in a different video about how to store the value of big G into your calculator using the STO function, STO, okay? And just typing in 6.67 times 10 to the negative 11 on there. It makes it a lot easier. It's just fewer things to have to type in, okay? Okay, the next question, so that is part A. Part A. Now we're gonna move on to part B, and now we're gonna see Sally's, it says calculate Sally's gravitational field at that distance. So the idea is, here is Sally right here. Mark her off in green here. And she is giving off a gravitational field, just like the Earth does, just like the moon does, just like the sun does. And that field is all around her. And the field gets smaller and smaller the farther out you are. So the basis for this gravitational field is how far away the object, Frank, is from the object giving off the field. Okay, we'll call Frank the test mass because his mass is actually not important in this situation. So we're interested in how far away the test mass is but also how big is the mass giving off the field. Okay, that comes together in this equation here. We're going to say gravitational field, which is little g, is, yes, as in the 9.8, right? This is how we got that. We can solve it two different ways. I'm going to solve it the more standard way. Big G, remember little g and big G are different, times mass of Sally divided by r squared. Okay, let's go ahead and plug these in. I don't need to rearrange anything. So 6.67, I'm going to write it as capital E, negative 11. That's how you should do it in your calculator. Ooh, forgot to have units. Newton meters squared per kilogram squared. And then times the mass of Sally. We don't care about Frank's mass. We only care about Sally's mass because she is the one giving off the field. And divided by the distance Frank is from her. Remember, Frank is the test mass. So once again, 0.75 meters, and then make sure to square that. Now, I didn't mention this before. I should go back and check the units here. The reason why the units are so strange, notice the kilograms and kilograms, those two cancel out with kilograms squared. And then when this meters here gets squared and we divide that, that cancels that out. And that's how we're left with the units of newtons for force. In this particular case, in green, where we're looking at the gravitational field, let's go ahead and show how, let's see, meters squared get canceled out there. Kilograms, only 1 kilogram. Oop, did I not mark that? Silly me. Okay, this should be squared. The square cancels out here. So this is going to be newtons per kilogram. So those are going to be the units that we have. Anyhow, let's go ahead and punch that into our calculator, and we get 1.9 times 10 to the, which I'm just representing as a small size capital E. That's what our calculators do. Negative 9. And we can use newtons per kilogram if we'd like. We can also realize, hey, isn't a Newton is really just kilograms meters per second squared, right? So if I divide newtons by kilograms, I'm just going to be ending up with meters per second squared, okay? Or meters per second squared. And that's what we know from earlier on in the year when we would say, oh, acceleration due to gravity on the Earth is 9.8 meters per second squared downwards. Or on the moon, 1.6 meters per second squared downwards, and so on. Okay? We could also have used a slightly different version of this. We could have said gravitational force is equal to m times g, right? This mass here is going to be the test mass. This is going to be Frank's mass. Okay? Just like if we wanted to figure out the gravitational force acting on us from the Earth, we wouldn't put in the Earth's mass there. We put in our mass. So I'm going to rearrange this, solve it for g. So in other words, I'm going to divide by Frank's mass on both sides. Let's give ourselves a little more space. So there's this gravitational force. That's what we had up there in purple. And then divide through by Frank's mass, and we'll just put in this guy right here. We'll put in 2.3 times 10 to the negative 8 newtons divided by Frank's mass, not Sally's mass. Remember, we're putting in the test mass right here. So the test mass, that's Frank's mass, is going to be 12 kilograms. So this is really, really important that we keep track of which mass is which. Because it turns out Frank's mass doesn't matter. It doesn't matter if Frank is 12 kilograms or 6,000 kilograms. Well, we wouldn't want something much larger than the mass giving off the field. But as you can see, Frank's mass gets canceled out because Frank's mass is involved in this gravitational force, what we're essentially doing is canceling out Franck's mass. Okay, that's why I wanted to show you this version first, because this is the more standardized, it's the more obvious one. It says, oh, I only care about the mass giving off the field, Sally's mass. Okay, all right, so there we are. That's with Franck and Sally. Let's move on to question number 2. Gravitational force between two electrons 1 meter apart is 5.42. So let's go ahead and list off some variables. Okay, so I've gone ahead and listed out the information. I'm looking for the mass of the electron. I know that they are 1 meter apart. That's the R value, the orbital radius between them, right? You can think of it like that, or more to the point, the radial distance. That would be a better way of saying it here, because they're not really orbiting each other. That's for when we're talking about planetary stuff, but you can still apply it. Anyhow, the R value there is 1 meter, and the force between them is super duper tiny. Now I'm going to clarify that this is gravitational force, as not the same thing as electrostatic force. The electrostatic force between two electrons is actually a lot bigger than the gravitational force between the two electrons. Okay, let's go ahead and choose our equation. Well, it's going to be the same equation as before, right? Gravitational force is equal to big G times mass 1, mass 2. Well, it's just the same masses. Mass of first electron and then mass of the second electron. When we write electron, we say E with a negative sign. That's just standard. And then divided by the R squared. Well, I already know the force, and I already know the R, and I already know G. I'm really trying to figure out the mass of one electron. Well, keeping in mind that these two masses are really the same. So what I'm going to do is I'm going to rewrite this and say that it's, oops, give myself a little more space. I'm going to rewrite this and say gravitational force equals big G times the mass of an electron squared, because it's mass, the masses are multiplied together. Say, okay, what am I going to do? Oh, I see. Now I'm going to solve for that. So I'm going to multiply both sides by R squared. And then I'm going to bring this up here. And then I'm going to bring the big G down. Okay, so mass of the electron squared equals gravitational force times R squared divided by big G. Okay, hopefully you saw the rearranging. And then finally, I don't want the squared, I want just plain mass. So mass, I'm going to take the square root of both sides. Grav force times R squared divided by big G. If I wanted to take out the R squared, I could do that. I could say R squared and then times the square root of force over big G. In fact, let's do that. Why not? Mass of an electron equals R, because I took the R squared out of the square root sign, right? Fg divided by big G. Now I'm just going to go ahead and plug in, okay? R, well, that's just 1.00 meters. Okay, and then times the gravitational force, but that's inside of a square root, 5.42 E negative 71 newtons. And then over big G, remember big G is 6.67 E negative 11. And then the weird units, Newton meters squared per kilogram squared. Let's extend that there. Okay, the meters squared, when they come out of the square root sign, they'll cancel out that, and the newtons cancel out there, and I'll be left with 1 over kilograms squared inside the square root. Well, 1 over something is just, that's something. So it's going to be kilograms squared inside that square root. And then I'm going to take the square root of that. Let's go ahead and pop that into our calculators. Okay, and when I get that, I'm going to get mass of the electron is square root of 8.1259. I'm just going to have some extra digits on there. And as I mentioned, kilograms squared. Okay, now I'm sorry, silly goose. I forgot the times 10 to the, right? That's huge. E, negative 61. What? And then kilograms squared. Okay, look at that. Look at that weird number. I still got to square root this, but I wanted to make sure that we were getting to the right spot here, because it's very easy to make mistakes in here, especially when we're not properly typing things into our calculator. If you were to just do like 5.42 times 10 caret negative 7.1, okay, that would have probably been fine. And then but then you type this in, 6.6710 caret negative 11. No, that's going to mess things up, because what you're actually telling the calculator is multiply these and then divide by not this whole value, but divide it only by 6.67. And then you're saying multiply the entire value by this. Okay, so if you want to put parentheses around this, you can go ahead and do it, and you can write it like this. Okay, but if you want to bypass the whole parenthesis thing, that's why I was saying use the second comma. Use it, and it would look like the small size capital E. It takes the place of this. Small size capital E on our calculator would take the place of this. Okay? Anyhow, let's get the final answer. Mass of an electron, just got to take the square root of that guy down there, that 8.1259 10 to the negative 61. That's going to be 9.014397, so on. Okay, I'll just do this. E, that's in times 10 to the negative 31 kilograms. Okay, which if you look up the mass of an electron, hey, that's what it is. Physics, it works.